again. So the last thing what we were left yesterday was the settlement questions. The settlement of consolidation settlement. So for consolidation settlement, the last thing for the foundation design is the consolidation settlement. So for consolidation settlement, we have three types of cases. The first one is our soil is normally consolidated. The second one is the soil is over consolidated. And not in over consolidated, we have two different cases. So we'll look towards these cases. First, we have this normally consolidated clay. So what this means that, for example, if we draw this consolidation test chart, so it is something like this. So in horizontal axis, we have some load, which we can call as P. On vertical axis, we have this void ratio E. So in this chart, so where the slope of the chart changes, this slope changes. We call this pressure as, this is pressure or this is stress. We call this stress as sigma C, or pre-consolidation pressure. Okay, so this where the slope of the line is changing, we call this as pre-consolidation pressure. This curve is, so one moment. So where the slope of the line changes, we call this as pre-consolidation pressure, sigma C. The line before that is, we call this as recompression curve, recompression, and the line after it we call as Virgin curve. So these two curves are given. So the slope of decompression curve we call this as CR decompression, and the slope of Virgin curve we call this as CC. So this is basic consolidation test. Now for normally consolidated clays, if the sigma C value is approximately equal to sigma Z naught value, the initial overburden stress uh, sustained by the soil layer, that is sigma Z naught. If that is approximately equal to the pre-consolidation pressure sigma C, we have plus minus 20%. Plus minus 20%, we have limits. So that is approximately equal. So we call that soil as normally consolidated clay. So if that is approximately equal, that sigma Z naught is also this one. Is also sigma Z naught. So we call this as normally consolidated clays. Now in over consolidated clays, the curve is the same. First one, second portion, and this where the slope changes. This is sigma C. Now in normally consolidated clays, the thing is our sigma Z naught, the pressure sustained by the soil layer, is very much less than sigma C. So if this is the pressure sustained by soil in the past, there is sigma Z naught or effective overburden stress. So if it is very much less than sigma C, then we call this clay as over consolidated clays. So that clay is over consolidated clay. Now we have two cases in this question. So first case and second case. So after we have applied a load on this layer, sand layers, for example, we applied a load of delta sigma. So we have two cases. So either sigma ZF, that sigma ZF, oops. So sigma ZF is equal to sigma Z naught plus delta sigma. Sigma Z naught is the initial overburden pressure without any application of load. Delta sigma is suppose we are constructing a building or something foundation, placed a foundation on the soil that increase the stress on the soil. So that is delta sigma. So adding both these two, we'll get the final pressure on the soil as sigma ZF. So we have two cases. Either sigma ZF is before the sigma C, or either sigma ZF has increased more than this value, sigma C. So we have two cases. The first one is, and the second one is. If I suppose look at this question, what they have, just what they have denoted these two parts. So now overconsolidate case 2. Yes. So they have called this sigma ZF more than sigma C case 2 and the sigma ZF less than sigma CS case 1. So sigma ZF less than sigma C or sigma ZF greater than sigma Z. So there are two cases in overconsolidation. Sigma Z naught would always be less than sigma C, that is sure. And the first one case is that after the application of stress, either the sigma ZF would increase or not. If the sigma ZF is below the sigma C, even after increasing, applying this delta sigma load, then we call this as case 1. And if the sigma ZF has increased more than the sigma C, we call this as case 2. So for normally consolidated case, so whatever, so the so our settlement equation would be H times CC over 1 plus E naught times log sigma ZF over sigma Z naught. So this is our basic equation for settlement. Settlement is equal to H times CC over E naught. Why CC over E naught? Because we are actually at this pressure. This is sigma Z naught. So we'll move in this version curve. So the slope will use as sigma H into CC over E naught times log of ZF over Z naught. So the log of ZF over Z naught, the final pressure over the initial pressure, that is settlement equation for the first case, for the normally consolidated case. For the first case of overconsolidated, if we look at this curve, so we are moving from this stress to this stress. So we are only lying in this CR or decompression curve. We are not moving to the second curve. So this formula would exactly be the same, just the difference would be H into CR over 1 plus E naught. Just the difference would be CR coefficient here we'll use. The previous one we use the CC coefficient into log of sigma ZF over sigma Z naught. So this is fine that in the normal consolidated case we use the coefficient CC, in the overconsolidate case we use the coefficient CR. Now in the last case, if we look at this portion that we are moving from this much stress to this much stress, we are moving from the first line to the second line. We are actually moving to moving in the both lines. So we can call this settlement in the second case as the sum of these two both two settlements. So the sum of first settlement would be that would be H times CR or 1 plus C naught times log of, here the delta F is, this is F final pressure for this curve, that is sigma C over sigma Z naught. The final pressure for this first curve plus the second curve C over 1 plus E naught times log of sigma ZF over sigma C. So this is final pressure for second curve and this is initial pressure for second curve. So we have actually divided this into two parts just. So just we have to memorize these formulas. Any issue in this sort should be moved to other numerically. So if we look at this Michael 11.5, so we are given this 3 meter fill is to be placed CCCR 11.5. So CC point 4.4, point CR is 0.08, and E naught 1.1, and sigma C, the pre-consolidation pressure as 70 kPa. So the soil profile is, so we have 3 meter proposed fill on the top. So if I draw the proposed fill later on, so first we have these 5 layers. So we have this water table here. This is first layer, and the 10 meter layer second layer. This is 10 meters. So the first layer we have of 1.5 meters, second of 2 meters, 1.5. This is of 2, and this is of 10 meters. So we can divide it into smaller parts. This is very large layer, so we can divide into smaller parts. So if we divide into 3 parts, so we can get the layer heights as 3 meter, 3 meter, 6 meter, and the last one as 4 meters. So we can divide this layers as like this way. So I haven't drawn the fill yet. We'll draw this onwards later on. The gamma first layer is 18.5. Now submerged gamma in the water table is 19.5 gamma submerged, and the gamma submerged for the clay layer is 16. So these all gammas are given. Now we have taken a sample at 4 meter depth. We call this point A. So we have taken this 4 meter sample here and this A, and perform consolidation test on it, and we'll get this, all this, we got this, all these values. So first of all, what we have to check, we have to check whether this clay layer is normally consolidated or over consolidated. So this is clay layer, this is a sand layer. So sand layer we can simply ignore. The consolidation does not occur or is very much negligible in sand. In clay layer it is important. So in clay layer we have to check whether it is over consolidated or it is normally consolidated. So how we can check? We can simply compare sigma z naught at A with sigma c. So if they are approximately equal, we can call this as normally consolidated. If the sigma z naught is very much less than sigma c, we can call this as over consolidated. So the first portion, we can find the sigma z naught at A. Sigma z naught at A is equal to 18.5 into 1.5, the top layer, 18.5 into 1.5 plus the gamma submerged we have to find. So 19.5 minus 9.81 into 2 plus 16 minus 9.81 into 4, because the sample is 4 at 4 meters. A is at 4 meters. So if we get calculate this value, we'll get some value very much closer to 70. I think 68 or something. So we'll give off C 72. We'll get the value as 72. So the sigma C was 70 kPa. So this is very much equal to sigma C. So that means our soil is normally consolidated. Fine. How we have to check uh, whether the layer is consolidated normally or over consolidated. So after this, what we have to find, we have to draw this table. So we have this layer. We have 5 layers, I think. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have height of each layer in meters. So we have 1.5, 2, and 3, 3, 4. And sigma z naught, sigma zf, cc of 1 plus e naught, and finally the settlement. So SC, so delta C consolidation settlement. So first we have this sigma z naught. So sigma z naught is the overburden pressure at the middle of the layer. So for example, this is the first layer. So the overburden pressure at this layer would be simply 18.5 into 1.5 by 2. 18.5 into 1.5 by 2, because the whole layer is 1.5 meters thick. So we'll get this 18.5 into 1.5 by 2. For second layer, we'll get this in the middle of this layer. So the whole first layer, 18.5 into 1.5 plus the half of the second layer. So 19.5 minus 9.81, because it is under water table, into this thickness of layer 2 by 2, this thickness half. And like the third, in this third case, we'll get 18.5 into 1.5 plus 19.5 into minus 9.81 into second layer thickness plus 16 minus 9.81 into 3 by 2, this half layer thickness. So this way we can get the sigma z naught for each, uh, so for the middle of each layer. Any issue on this? So if there is no issue, the last the we have to find sigma zf. For that we have to find the delta sigma. Delta sigma is simply the proposed fill. Proposed fill is 19.2 and it is 3 meter thick. So the delta sigma would be 19.2 into 3. So I have not drawn here because it may cause confusion. So simply delta sigma is 19 point, or this is about 60. So about 60. So whatever the values of this are, simply add 60 in that plus 60 and we'll get this sigma zf value. Simply add sigma z naught plus delta sigma, we'll get this value. Find sigma zf. Now the last is the CCO1 plus E naught. So we are provided this CC, we are provided this E naught. So 0.4 over 1 plus 1.1 will get this value, something like 0.1, 0.19 and 0.19. For sand, our value would be given, in this case it is given as 0.008. So the sand will be given CCO1 plus E naught. For the clay we have to find it ourselves. So afterwards we have all this. So the formula for consolidation was H times CC over 1 plus E naught times log of sigma ZF divided by sigma Z naught. So simply H is this first column. This is H. So for first layer, it would be consolidation would be 1.5 times CCO1 plus E naught. So CCO1 plus E naught we have calculated as 0.008 times log of sigma ZF. So sigma ZF we can assume this as 120 something value, or sigma Z naught as 60. So if we simply multiply them, we'll get the settlement in that layer. Do this for all layers, add that settlement, and we'll get the total settlement. So this is how we can get the consolidation settlement. Any issue in this question?
No,
No. So for the second question, now look at this question. We have given these two layers. See this clay 1, we can call C1. This is clay 2, C2. So this whole question is exactly the same. Just the difference is we have to find this. We have to check whether the clay layer, each clay layer is over consolidated or normally consolidated, over consolidated or normally consolidated. So what we have to do, first calculate sigma z naught of A, compare it with sigma c of A. So sigma c of A is given as 101. So calculate sigma z naught of A. Sigma z naught of A was 55. So our 55 is very much less than sigma c. That means our layer is over consolidated. Again, in the same way, find the sigma z naught of B compared with the sigma c of B. Sigma z naught of B was, sigma z naught of B is 198, I think. So sigma z naught of B is 198. On the other case, the sigma c is given in this question as 510. So that is given as 510. So it is again very much lesser than 510. So that means this is also over consolidated. That is how we have to find whether the soil is normally consolidated or over consolidated. Now after we have found that these both layers are over consolidated, now we have to determine which case of over consolidated they are. So for that case, we have to find the sigma ZF for each layer. Sigma ZF is simply sigma Z naught plus delta sigma. Delta sigma is 20.3 into 8.5. Delta sigma is 20.3 into 8.5. So multiplying them, the delta sigma for first value is 227. So ZF is 227. It is less. It is greater than sigma C. So that means our case is that sigma ZF value have increased more than sigma C. So the case is this is our case. So sigma ZF value has increased more than sigma C. So our case is 2. In the second question, the sigma ZF value is 370, while the sigma C value is 510. Sigma ZF is 370. It is still less than sigma C. So our case is first case. So why we are doing this case? So just when we are going to make this table, so which quotient we are going to multiply, just for this that purpose we are doing these cases. So for first layer, for example, this is up till the first layer. So for first layer, we divide it into three parts, h and some values. We calculate sigma z naught, and we calculate sigma c for that. Now, how to calculate sigma c for middle of the layer? We can calculate over consolidation margin. The sigma m is the over consolidation margin. So that is sigma c minus sigma z naught. So sigma c was our 101 and sigma z was 46. So simply add 46 in these values, sigma z naught will get this sigma c value. Fine, that simply add sigma m in the first column in the sigma z naught value. We'll get the sigma c value, and simply add delta sigma in the first column, we'll get the sigma cf value. Sigma, the over consolidation margin in the first column becomes sigma c. The change in pressure in the first column added becomes sigma zf. So now, because we know this is the second case, so our second case, the formula is longer one. So h times cr over 1 plus e naught log of sigma c over sigma z naught. So why we are calculating sigma c in this particular case? Because in this formula we are requiring this sigma c. So that is why we are calculating in the case 2 of consolidation only. Not in the case 1, not in the normally consolidated. We do not need this column. Plus h times cc over 1 plus c naught times log of sigma zf over log of over sigma c. So just simply use this equation, plug in the values cr and cc, calculate the settlement. Similarly, in this case, this was consolidation case, OCC case 1, this was OCC case 2. So in this OCC case 1, the only difference is cr over 1 plus c naught times log of sigma zf over sigma z naught. So h times. So only difference is cr, we are going to multiply it by cr values. So no need to calculate these values, these are not required. Multiply them, get the total settlement. Any issue in this?
No, but
No, so if we move to this problem, in this problem there is no overburden pressure. That means delta sigma is 0. There is no overburden pressure. Just the difference is the groundwater table changed from this initial value to this final value. The groundwater table has reduced. Just this effect occurred. There is no overburden pressure. So this is a simpler case. What we have to do for these things. So now we are given these values at point A. This is point A. So at point A, at this depth, first we have to check this layer is normally consolidated or over consolidated. Again, the same thing. We have to check this normally consolidated or over consolidated. So if we calculate sigma z naught here, that is 2623, which is approximately equal to 3000. So if we multiply it by 1.2, because we can take 20% margin on both sides, so it becomes approximately 32 or something. So this is approximately equal to sigma c, that was 30,000, 3,000, sorry. So we can call this as normally consolidated. Now the table layer H the same. Now there is sigma z naught values at the middle of the layer. Now there is no adding sigma delta sigma in this because delta sigma is 0. How we have to find this sigma zf? We have to just assume this watt table not here. We have to assume this watt table here. We calculate sigma z naught by assuming watt table here. This was for sigma z naught. But for sigma zf, we are going to assume watt table at here. We are not going to assume watt table at the top. So again, we have to calculate the overburden pressures. These are again calculated as the overburden pressures, but watt table in this case is below. So Cc of 1 plus C naught is given. Multiply because it is normally consolidated. It is formula is H into Cc of 1 plus C naught. Log of delta sigma zf over sigma z naught. We'll get this total settlement. And this is inches. Whatever settlement comes, it is in feet because the H is in feet multiplied by 12. So we'll get this value is in inches. Similarly, in the previous cases, we multiplied by 1000 at the last. So to get settlement in millimeters. So an issue in this third case.
No.
Okay, so the last question for this settlement is this type. So in this case, they have not proposed a fill on that. If there was a fill, we calculated the change in pressure simply as gamma time depth of fill. So whatever the fill was, we simply multiplied by the depth, so we can get the change in pressure. But now in this case, they have placed a small circular footing on the top of the layer, on the top of the sand. This fill was of infinite extent, so that is why we are assuming constant pressure. Now we are, because we are placing a small settlement on this, its pressure would reduce in the downward direction. So just the difference here would be how we have to calculate the pressure of this one and how we are going to reduce this pressure. So how we have to calculate this pressure? First of all, they are saying that the empty mass of this is 300,000 kilograms, and the water in this would be 9.5 meter deep. So simply the pressure exerted by this would be, you can call this as delta sigma. That would be simply as 300,000 This is in kilograms. If we want to convert it into kilonewtons, so multiplied by 9.81 divided by 1000. That way we can get the answer in kilonewtons. We divide this whole by the total area of footing. So area of footing is, they are saying this is a cylindrical. So this is a cylinder. So for cylinder of 20 meters dia, so the area would be pi by 4 into d square. So the d is 20 meters. So it is a cylinder. So the area is circular. So it is pi 4 into d square. This is the empty weight of the footing or the steel cylinder, and in this cylinder water will also be placed. So we have to also count for the weight of the water. So the weight of water would be gamma water times height of water. Gamma water in kilonewtons is 9.81, and height of water they have provided as 9.5 meters. So simply multiply it by and get this delta sigma value as approximately 102 kilopascals. So this comes about almost 102 kilopascals. No need to do this, all these things they have written. Simply use this formula and calculate delta sigma value. Now after doing this, check whether the soil is normally consolidated or over consolidated. So in this case, they are saying that use the example in 11.5. So example 11.5 we solved here. This was 11.5. So they are saying they use this data. Use this data. So simply in this case, we know the soil was normally consolidated. So we do not need to do that again. But in the paper, because uh, they would not say that the soil is normally consolidated or over consolidated. So we have to do the procedure in the paper. So again, the table comes the layer height sigma z naught. You must know about this. Now we have to determine this, how much this reduction would take place, how much this reduction of this 102 kilopascal would take place. because this is a small footing. So small footing reduction will take place. If they are saying that a fill is placed, so we assume that it's of infinite extent. So in that case, no reduction will take place. But if they are square footing or strip footing or circular footing, any of the footing, we are going to reduce that value. So how we are going to reduce that value? First, we calculate the ZF, that is the depth in the middle of the layer. Now, if we move towards the charts, the settlement charts. So I think this is a settlement chart. Yes. So this is stress charts for circular footing. This one, the stress charts for circular footing. So if you look at this picture, so they are saying that the depth of the point where we have to find the stress is Z, the radius of the footing is R, and the X is if the point is the point where we have to find the stress is not directly below the footing. So we are taking X in this case as 0 because we are assuming the point is lying exactly below the footing. So X is 0. So Z we have is for the Z case they have drawn a table. So where that went, this one, yes. So for the ZF value they have drawn this table. So if we look at this thing, how we get this ZF value? So we have 3 meter fill on the top. So this was filled on the top. So the height of the middle of the first layer would be ZF. So the height of the first layer would be 1.5 meters. The height of the second layer would be second layer ZF. So this would be 3 plus 1.5 by 2. So 3.37, 3.75. 1.5, 3.75. The third layer would be this middle of the layer height. That is 3 plus 1.5, 4.5 plus half of 2. So 1. That is 5.5. In this case, in this way, they have determined the ZF value for each layer. Now using the ZF value in this charts, in the x-axis we have Z over R. So Z value we can assume for Z value for the we can assume for the third layer as suppose 5.5 meters. We are doing this for 5.5 meters. So 5.5 meter is our Z value, and diameter was remember 20 meters, so radius will be 10 meters. So approximately 0.55 value will get Z over R. So in the horizontal direction, locate 0.55. So that is 1, that is 0. So approximately 0.55 would be here. So I think that is here. And our x value, these curves are from x over R. So since our x is 0, so our curve would be 0. We'll use this 0, 1 curve, this 0 curve. So for 0.55 value, this curve, we'll get this approximately 85. So our I value is 0.85. Actually, we can draw another column in this here of I. So in the third layer, we can draw this of I as 0.85. I is the influence factor. Now delta, the sigma z reduced would be simply sigma z r would be delta sigma times I. So delta sigma we have 102 times 0.85, that would be 102 times 0.85, that is 86.7. So they have written 90.6, so approximately that's fine. So we got 87, they are written as 90, so that's fine. That curves are approximate, so that depends on reader's discretion. So after getting this whole table from the curve, simply add this reduce with the sigma z naught to get this sigma zf value, and the rest of the table is same. First one is over consolidated, so they have placed on the CR value. The rest is normally consolidated, so they have placed the CC values. Use the formula, get the deflection, and that's all for consolidation. Any issue in this? So if I do a summary of this, first we have to check the case, then we have to determine uh, whether the soil is normally consolidated or over consolidated, and then accordingly we have to apply that formula, whichever the case was. Any question in that part?
No, brother.
No. So any question in the whole course, or should we end?
Yes, brother. Last portion of foundation of
Yes.
Sir, Sir Hassan Mushtaba, I think. The group
Last
files,
group files. Yes.
actually,
Group files.
the, the initial settlement, there is a three method. Which method we should follow, actually?
Which method? Okay. If you look at this, we have three methods exactly. We have Jambo method, we have Timoshenko, and we have uh, Schmertman. So if we look at this one, so if you look at this, I was also actually looking at that also. I was also looking that which method should we use. So if you look at that, so they are saying that for these methods, Timoshenko, Schmertman, they are used mainly for sands. So if the soil is sandy method, sorry, if our soil is sandy, the method we are going to apply is Timoshenko or Goodyear, Timoshenko or Shemetman. And if the soil is clay, the settlement of saturated clays, we are going to use this Jambo method, like in the example. So in example, they have used Jambo method, and most probably because we have to find the consolidation settlement as well. So only clay layer would be given. So uh, there is more focus on this method, Jambo method. So is this fine that if the layer is sandy, then Shemetman or Timoshenko? Otherwise, clay. So we are going to use Jambo method. So most probably the method chart would be given in the table in the paper. Sorry. So we can only apply that chart. So any more issue?
Brother, most
So for
probably, I
just
think
remember,
in foundation part,
yes,
so most probably in foundation part, I think just two questions will come from that two parts, huh?
just to we have foundation part of 20 marks. So I think maybe 6 to 8 marks would be from consolidation, and the rest 12 marks would be from these files. So maybe two question would become yes. Maybe some one from this file and one from this group file. I think. Otherwise, maybe one large question may come of the whole group file. So that depends upon sir. I don't have much idea. So any more?
Bro, actually, if you put to send it as the last example of group file settlement, the solution of that.
The solution of that. Okay, I'll share. I'll share all the examples in the slides. I have done that.
Okay, thank you.
All right. So should we end this meeting? Yes.
On my side, yes.
All right. So let
Yes,
me
brother.
stop the
Thank
recording.
you.